And let us begin the lecture number 8. Lecture number 8. And yeah, today is exciting day. Today we start the new chapter. I guess it's supposed to be chapter number 3. And let's call this one Maxwell equations in matter. Maxwell equations in matter. Yes, thus far we discussed the Maxwell equations and the electromagnetic fields in free space. And of course, we just touched this question about the resonators of electromagnetic field, but the resonator itself supposed to be empty, right? So containing no matter in it. And now we're gonna discuss what happens when the system gets any sort of matter, some materials. And of course, the presence of these materials cause different change to electromagnetic field. And the question of today's lecture is to define how the presence of matter changes the electromagnetic field. And we're gonna start with the writing down the Maxwell equations in free space. So basically what we know so far. So first of all, we recall this equation for the divergence of electric field, and is given by the charge density over epsilon 0, right? And if I integrate this one over some volume, it will give me the equation for the flux of electric field through any arbitrary surface, and it's equal to the total charge in the system. Another equation was for the divergence of magnetic field, and it's equal to 0. The manifestation of the fact that we have no magnetic field, no magnetic charges in nature. Another equation was about the curl of electric field, and it's given by minus dB over dt, right? And finally, curl of magnetic field. And it's equal to mu 0 current plus mu 0 epsilon 0 dE over dt. Yeah, we spent some time for discussing these two terms, right? And these two terms are currents. The first one is the current of free charges. Like, for example, in metals, we have free electrons. Okay, and this JC describes the current caused by these free electrons. The properties of such substances, like metals, to conduct currents is given by the conductivity, sigma, conductivity, and the current is proportional to electric field. So this is the first one. The second one was the displacement current. Displacement current. The current that has been introduced by Maxwell to the theory in order to make it symmetric, right? For example, what I mean by symmetry here. So if you look at this one and at these two equations for the curl of electric and magnetic field, right? So the curl of electric field has this time derivative of magnetic field on the right side. And before Maxwell, this equation, the second one, didn't have the displacement current. Yes, the displacement current, and only the conduction current. And and these two were asymmetric, right? So first one says that the change of magnetic field creates electric field, but the second one says that only current creates magnetic field, but it's not the case. And we return this term here back. So we restore this symmetry. So the change of electric field also creates the magnetic field. All right, so this is what we know so far. And now we discuss how these Maxwell equations and how the electromagnetic field changes as it comes to any sort of materials. And basically our goal is to introduce a number of material parameters that are used to describe the interaction of matter and the field. And as the first one, we discuss the case of dielectrics. So the dielectric, like perfect dielectric, is a system without free charges. So we require no charges. And if the system has no free charges, then the current density of free charges is equal to 0 along with the density of these charges also equal to 0. So no charges, no free charges. At the same time, all charges are bound. Okay, so for example, if I take a microscope and zoom into such a perfect dielectric, I will see something like this. I will see some nuclei, okay, and these nuclei, they are typically very heavy. It's very hard to, and they interact also between each other. They form the crystal structure of such a material. So they don't move, they don't contribute to currents. At the same time, these atoms, they get the electrons that orbit around the nuclei like this. So electrons, and these electrons are bound to the nuclei, to the atom, and they don't move too far from the atom. The only movement they can do, they can jump from one state to another state, right? But they still move around their own atoms. So these electrons, they don't create any current. They don't contribute to currents. Okay. But at the same time, this is a system of nucleus with one charge, positive charge, let's denoted by Q1, and electron, right, with another charge Q2, negative charge. And of course, if I apply the electric field on this system, the electric field causes the electron move to one direction, the nucleus either stays the same or moves to another, to the opposite direction. And in the result, the system becomes polarized. Okay, so this is the process of polarization. In order to describe this process of polarization of one atom, we introduce the concept of the dipole moment. Traditionally, it is denoted by D vector and is equal to Q1 R1 plus Q2 R2. So R1, R2 are the coordinate vectors. Coordinates of Q1 and Q2. Okay, and Q1 and Q2 are absolute the values of the charges. Okay, so for the system that we draw on the left, Q1 equals to minus Q2 if Q1 equals to minus Q2, then we come to this typical definition of the dipole moment. If we also introduce the dipole shoulder L, which is equal to R2 minus R1, right? The distance, the separation between two charges. We come to this well-known formula of dipole moment equals to the charge, either nuclei or electron, times the dipole shoulder L, the separation between charges. Okay, so this is the dipole moment. So this is about one dipole moment of one atom. What if we have a system of many atoms? Well, if we have a system with n atoms per volume, per unit of volume, then the total dipole per the volume unit is known as the polarization vector, is denoted by P capital. Okay, and it's equal to the number of atoms times the dipole moment of each single atom. Of course, atoms can be different, and one needs to average these dipoles and the number of dipoles per volume, average over some parameters, etc. So here we don't discuss these things. So my goal is to basically introduce the material parameters that we'll need for the simulations, so you understand what they actually mean, rather than rigorous introduction to Maxwell equations in media, in matter. People publish very thick books about how rigorously describe electromagnetic field in different materials. So we try to skip all those and just focus on the essentials. Okay, so applying electric field creates polarization. So yeah, let's polarization. Applying electric field creates polarization, and appearance of the polarization vector in the system. Let us connect now the polarization with the density of bound charges. So to do so, let us consider arbitrary volume of some material, materials dielectric, of course, and the material is immersed in the electric field. Okay, and this electric field causes the electrons move to the negative direction of the field. So for example, electrons somewhere here will tend to go to, not really go, but the orbitals of the electrons will deform. They will be deformed, they will be stranged in the negative direction of the electric field. So this one will tend to go this way, these two will go this way. And so some electrons of some atoms on the boundary of this unit volume, they will go in, but some others on the opposite boundary, they will go out. Okay, of course the total charge of this won't change because the number of electrons that go inside of this volume is equal to the number of electrons that go outside of this volume. But for example, for the number of electrons that go out, we can write the charge of this, the total charge of these electrons. And since they go out, we put minus. And then what we do, we integrate the polarization, because this creates polarization. All right, we integrate the polarization over the surface of this unit volume. So the C is the or S vector is the surface of the unit volume. P is polarization. So I require that my polarization P is defined in a way that if I integrate it over some surface, and so I calculate the flux, right? The flux of the polarization vector through this surface. So this flux of polarization vector through the surface is exactly equal to the charge that goes out. Of course, there are charges on the opposite side here that go in, and it's gonna be exactly the same formula up to this sign. It will be plus before the integral. Okay, so why we use this? Because now I can use the divergence theorem to represent the integral over the enclosed surface to the integral over the volume from the divergence of polarization over the volume. Okay, and this is on one side. On another side, this is Q, this is total charge, and the total charge is given by the integral of the charge density over the same volume. And since this is not the conducting charges, this is bound charges, I put this index B here. So these two integrals, they equal, and they are taken over the same volume, right? That means that this charge density is equal to minus the divergence of the polarizability. Oh, sorry, polarization vector. Okay, so polarization vector is defined in a way that if I take the divergence of the polarization, it gives me the density, the charge density of bounded charges in the system, in the dielectric. And now this formula allows me to introduce the dielectric to the first Maxwell equation. So the divergence of electric field is 1 over epsilon 0 rho charge density. But now I assume that this charge density is the bound charge density because I have no free charges. Okay, so I can substitute this rho B, and by plugging in this formula here. So what I get minus minus 1 over epsilon 0 divergence P. Okay, let me let me subtract the right side from both sides, and I get divergence E minus gives plus 1 over epsilon 0 divergence P equal to 0, right? So it's divergence from the sum of two vectors. It's equal to the divergence of this sum of divergences of two vectors is equal to the divergence of the sum of the two. So it's E plus 1 over epsilon 0 epsilon 0 P. And finally, if I multiply by both parts by epsilon 0, which is a constant, I came to this formula, divergence of epsilon 0 E plus P is equal to 0. So now I introduce the vector that we already used to, but in the free space it coincides with the electric field, but in the matter, in the presence of matter, it gets its own physical value, importance. So this vector D, which is equal to epsilon 0 E plus P plus polarization, and it's known as electric displacement field. So electric displacement field. This D field, you remember when we introduced it in the first place, it was D equal to E epsilon 0 E, right, in the free space. But that's because of free space. Free space doesn't have polarization. The polarization vector in free space is equal to 0. So this is for free space. In matter, if matter can be polarized, then we need to add this polarization to the formula of the electric field displacement. And the first, plugging this one to the Maxwell equation, we get the first one, which says that the divergence of D is equal to 0. So this is the this is the first Maxwell equation that is fair for dielectrics. Okay, if the system still has some amount of free charges, then I would write it the same way, but adding this term for free charges. Okay, so this true for any system, fair for any system. But so thus far we discussed dielectrics. So what is the, so we say that polarization is caused by electric fields, but what is the dependence of polarization on electric field? And in most cases, the polarization is just linearly proportional to the value of electric field. So we can write it something like epsilon 0, then multiply by some factor alpha E and times electric field. So this alpha E is known as electric polarizability. Electric polarizability, and this electric polarizability is not a function of electric field, right? It's a function of type of matter, is a function of frequency, other parameters. So this is something that don't depend on electric field. It describes the material, the matter itself. Okay, so usually it's fair that polarizability is linear on electric field. Of course, if the electric field becomes too strong, then the dependence is not like this. So we got some nonlinear effects. But in most cases, the polarizability is described by this formula. So let us plug in this polarization, which, by the way, deserves to be framed. Let's plug in it to the formula for the electric displacement field above. So we've got D equal to epsilon 0 E plus epsilon 0 alpha E. The same can be rewritten as epsilon 0 1 plus alpha E electric field. Okay. And finally, we can introduce one of the most important material parameters known as the dielectric permittivity. So I basically denote this guy in parentheses by epsilon, okay? And this epsilon is equal to 1 plus alpha E. It is dielectric permittivity. So if you, so when you start the simulations, when you prepare, when you design your numerical problem, you usually need to specify the dielectric permittivity of the materials, of the all constituting parts of the project. Okay, so that's, at the same time, dielectric permittivity is something that is measurable for various materials. So yeah, so this is one of the most important, dielectric permittivity. And yeah, so we introduce, having this dielectric permittivity introduced, the displacement vector is given by epsilon 0 epsilon E. Okay. So we had this formula for the free space. It was d equal to epsilon 0 E. Okay. So we notice that in the presence of matter materials, the effect on the d field is in replacing epsilon 0 by epsilon 0 times epsilon. And for example, examples of like dielectric permittivities that we can see in simulations. For example, for example, epsilon of water. I remember these numbers. For example, water in radio frequency, at radio frequencies. Okay, so the epsilon of water in radio part of the spectrum is around 80. And it's pretty large number. Okay. At the same time, if you measure the dielectric permittivity epsilon of water in optics, it's gonna be something around 1.7. So you see how strongly this permittivity depends on the frequency. And for example, epsilon of silicon dioxide, which is just glass, also in optics, is around 2.25. Very good. So introduction of the charge, the bound density charges here, right, allows us to introduce the polarization vector and and the electric permittivity. But what about the currents? So let us define the current density of the bound charges. To do so, we recall this equation for the charge density conservation, or sorry, the charge conservation rule. So it is the time derivative of the charge density plus the divergence of the current equal to 0. So we discussed this a couple of lectures ago. If you have a area with some charges in it, the charges can go out and some of the others can go in, right? And because of this moving of charges, the density of the charges changes, and the number of charges changes, and the density also changes. This is described by this time derivative of the charge density. And at the same time, this flux of the of the charges is given by the current density that these charges create. And the equation in this form basically states that the total charge in the system is conserved. Okay. So we can we don't have the free charges, only the bound charges, and the same logic applies like what we discussed here. Some of the charges go in to some unit volume, some of others go out. Of course, the total charge in the system don't change, but I still can apply this formula locally to any part of my system and write the equation for the charge density of the bound charges in this form. The bound charges density and bound charges current density equal to 0. So now I recall that charge density of bound charges is equal to minus divergence of polarization. Okay, and plug in this one to the charge conservation rule. So what I get minus d over dt, the divergence of P plus divergence of current equal to 0. The special derivative and time derivative can be exchanged, and I can write it this way: minus nabla times dp over dt equal to minus nabla dot current bound. Okay, so from here I conclude that the current density of bound charges is equal to the time derivative of the polarization vector. So we apply electric field, the material becomes polarized, and the change of this polarization in time creates the polarization current. So this is polarization current. Current. In contrast to the displacement current in free space, now we have this polarization current, which is created by polarizations of the atoms. All right. So now, since this is also current, we can add this current to the curl magnetic field Maxwell equation. Right. So what we're gonna get is nabla cross H is equal to, well, let's write this density current of the free charges, because if the actual material has some free charges, we of course have this charge density of the free charges. And then we have this term associated with the displacement current, right? And finally, this new one, which we just derived, dp over dp over dt. And I can look at these two, and can I combine the both? Yes, because this is simply the time derivative of epsilon 0 e plus p. And this guy in the parentheses is nothing but the vector d. Right? So finally, I can write the Maxwell equation for the second one, for the curl of magnetic field in this form, d over dt. Yeah, and since vector d is equal to epsilon 0 epsilon e, right, in free space, this is exactly the same equation that we used to use in the free space. And now everything, what changed is just we replaced epsilon 0 by epsilon 0 epsilon. And this is actually the like a rule. So for example, if you transit from vacuum to dielectrics or from dielectrics to vacuum, so let's write from vacuum to dielectrics. We just replace epsilon 0 by epsilon 0 epsilon. And the equations will be the same. Okay, so the presence of the dielectric leads to the change of epsilon 0 by epsilon 0 epsilon. For example, the speed of light, right? For the speed of light was, we saw this formula. The speed of light is given by 1 over square root of epsilon 0 mu 0. And now we can write the formula for the speed of light in the dielectric, in a material without free charges. And what we do, we just replace epsilon 0 by epsilon 0 epsilon. So it's going to be 1 over square root of epsilon 0 epsilon mu 0. Okay. Or I can rewrite it in this form. Epsilon 0 mu 0 1 over square root of epsilon, right? So this one is the speed of light. The speed of light. And we conclude that the speed of light in dielectrics is changed by the factor 1 over square root of epsilon. And usually epsilon is larger than 1. So the wave in dielectric is slower than in free space. Like the electromagnetic field in a matter slows down by the factor of 1, by the factor square root of epsilon. That's why this square root of epsilon is something important, and one can even measure this by measuring the the velocity of electromagnetic field in matter. And for this reason, we gave the name to this square root of epsilon, and we denoted by n with this wavy tilde, which is equal to 1 over square root of epsilon. So this is known as refractive index. Refractive index. So refractive index describes the how much the wave in dielectric slows down comparing to the free space. Okay. There is one important point left to discuss here is the point of the fact that epsilon is actually the complex number. So here, when I brought these examples of epsilon, where it was, yeah, here, I didn't mention that these actually complex numbers, but sometimes you can neglect the imaginary part. But this is not the case in all other scenarios, all other materials. And in general case, epsilon is equal to epsilon real part plus imaginary unit epsilon imaginary part. Like if you look at the database and see, for example, the epsilon of gold, you will see that the epsilon of gold is a complex number. And the same way, the epsilon of silicon, another important material for for technologies, is also a complex number. And even water or glass, they actually also complex numbers, but with smaller imaginary part. And this brings me to the question how I can take the square root of this complex number, right? Square root of real part of epsilon plus imaginary part of epsilon times imaginary unit. So what it is? It is the refractive index, and and from this point, I also assume that refractive index is also a complex number. Okay, and what I do, I just assume that epsilon real part plus I epsilon imaginary part is equal to some n plus imaginary part, let's say kappa, just another letter of Greek alphabet. Okay, so square root of complex number is equal to another complex number. Makes sense. But now this allows me to take the square of both sides. Okay, and it leads me to the following: epsilon r plus I epsilon I equals to n squared minus kappa squared plus 2 n kappa n kappa I, of course. Yeah. So this is the real part. This is the imaginary part. So we can comparing the right and left side of this formula. Now I can equate the real parts and imaginary parts. For example, this one is equal to this one. This guy is equal to this one. So n squared minus kappa squared is equal to epsilon r. And 2n kappa is equal to epsilon I. Okay, these formulas are also quite important, and in fact, there is the largest database for the material parameters of different materials is called refractive index.info, as far as I remember, and it contains the I guess the vast majority of the known material parameters of all materials, and the data, in a way, they present the material parameters, actually this refractive index n and kappa, not the epsilon real part and imaginary part. This is simply because n and kappa are much easier to measure. So there is a approach called ellipsometry, and one can purchase the system ellipsometer, which is ready to use. Basically, you can use ellipsometer for measuring the refractive index and this n and kappa. And then you use these formulas to convert n and kappa to real part and imaginary part of dielectric permittivity of materials. Because the software like CST, Microwave Studio, or others, they work with epsilon rather than n and kappa. So it's always nice to have these formulas and convert things from one basis to another basis. Very good. Now, what about this K number, this wave number? So we discussed in the beginning today that K number describes the how fast the wave changes in space as it travels along some distance. N was equal to omega over c for free space. In matter, what we need to do, we need to change the epsilon 0 by epsilon 0 epsilon, and it leads to renormalization or change the phase velocity from c to v, and we've got something like this. I put this tilde, assuming that this wave vector with wave number can be complex number now. So it's going to be equal to omega over v or omega over c times the refractive index n tilde. Okay. And substituting for n tilde, this n and kappa, we've got something like this: omega over c n plus I kappa. Okay. And if we expand the parentheses and multiply this omega over c by n and by kappa, we're gonna get some other parameters. We can call them k, the real part of the wave number, plus some alpha I. Okay. So this k is equal to omega over cn, and alpha is equal to omega over c kappa. Over c kappa. So why we do that? Because this wave number describes the way how the field propagates, how the plane wave propagates in medium. And let us assume that we are dealing with monochromatic wave described by this in this form. So the electric field is equal to the some amplitude, arbitrary amplitude of the field times the harmonic function e to the power of kz minus omega t. Right? This is the most general presentation of plane wave. Okay, we can rewrite it by parts in this form: to the power of I omega t times e to the power of I k z. And now I closely look at this part: e to the power of I k z. E to the power of I k z. So this k now is the k tilde, right? We denote it by tilde, assuming that it is actually complex number. So I substitute this, plug in this formula to this equation, and get e to the power of I k without tilde plus I alpha z, and expand the parentheses, and I get e to the power of I k z times e to the power of minus alpha z. Okay, so because I times I is equal to minus 1. Because I is equal to square root of minus 1. So this first term describes the variation of the field in space. Okay, and this k is multiplied by refractive index, and refractive index describes how slower the field propagates in the matter, in the material. So this exponential function here is multiplied by refractive index, and because of this, this term oscillates faster in space. Okay, let me maybe draw this something like this. So suppose I have a wave in free space. Like this. So this is electric field depending on the distance z in our case. Okay, and what is the wavelength of this wave? The wavelength is the distance the wave propagates over one period of oscillation. So this is one period of oscillation, and this is the distance. So this is the wavelength of the wave in free space. Okay, but now in the dielectric, this exponential function, this phase of the exponential function is multiplied by refractive index, and it means that the wave oscillates more times per the same physical distance. So it's gonna be, for example, something like like this. So this is in dielectric. The function of distance. Okay. So you can say that the wave is kind of gets squeezed, right, in the dielectric. It takes more oscillations per unit distance. Oscillations in space, not in time. Oscillation in time is described by the frequency. Oscillations in space described by k vector, k number. If you're talking about the three-dimensional space and arbitrary propagation, then k number is promoted to k vector. On top of that, we have this second term here, which is e to the power of minus alpha z. E to the power of minus alpha z for positive alpha is the exponentially decaying function. Okay, so and this one describes the amplitude of the field. So we conclude that the actual distribution of the actual propagation of the field will be something like something like this. Exponentially decaying amplitude. Oops. Exponentially decaying amplitude. So this is the e to the power of minus alpha z. This is decay. This is decay. What else? This is the this is the alpha 0 over n, the new wavelengths. And let us write this down like this. So in dielectric, the wavelengths shrinks by the refractive index, okay, and decays by this exponential factor e to the power of minus alpha z. So in dielectrics, the wavelengths shrinks by n. The wave decays by e to the power of minus alpha z. And I just remind you that alpha is actually omega over c, kappa, and kappa is equal to epsilon, imaginary part of the epsilon over 2n, 2 refractive index. So you see that another nice point, that the epsilon 0 imaginary part of epsilon defines the dissipation of energy. Dissipation. Okay, so epsilon, imaginary part of the epsilon defines the dissipation of the wave as it propagates through through the matter. And if the imaginary part of epsilon is 0, then we have no dissipation. If epsilon imaginary is 0, then no dissipation. No dissipation. Yeah, maybe last statement about epsilon is the fact that many materials, they actually are anisotropic. Let's write it as a note. Anisotropic materials. So anisotropic materials means that the properties of such materials, like the wave propagation, depend on the direction. Okay, for example, if I have the coordinate system like this, I have a piece of material like this. can be some sort of crystal. It can be, I don't know, like cooking salt, or it can be glass. Some types of some sort of glasses, they are anisotropic. So isotropic materials, they look the same from, I mean, the properties of these materials are the same in different directions. The anisotropic materials, their properties depend on the directions. And and the electromagnetic properties too. And for example, we have this formula D is equal to epsilon 0 epsilon E, which is which holds for isotropic materials. Isotropic. Because D is collinear with E. Like, for example, if we apply electric field in this crystal like this, then the vector D will be also direct like this. And then if I change the orientation of this crystal or change the direction of the electric field, the D will always follow this change so that they stay collinear. Okay, so this is the case of isotropic. Let me copy this. Put here. So this is isotropic. But what about the other materials where the applying of electric field creates this vector D, or in other words, polarization, creates polarization in a very different direction, like to this direction. And then when I change the orientation of this crystal or the orientation of electric field, will also change the vector D, but in some complex way. Okay, so it turns out that in this case, this dielectric permittivity must be promoted to the tensor. I write tensor with this hot top. So this is tensor now. E. This is tensor permittivity. So what is tensor permittivity? For example, in a three-dimensional case, like we have now, this tensor permittivity is given by matrix with some components like epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz. So it's going to be like this. And the product of the tensor with the vector should be taken like a product of this matrix with the vector E in the column way, like ex, uy, ez, like this. Yeah, and so now we have this 3 by 3 9 components of this tensor, right? But there is a theorem that says that any tensor like this can be transformed into in the main diagonals of the main axis of the tensor. So this one can be transformed to much simpler form, like this: epsilon 1 0 0 0 epsilon 2 0 0 0 epsilon 3. Okay, so sometimes the permittivity is anisotropic parameter, so it's described by the tensor. Do you have any questions thus far? Okay, if not, so do you guys follow me?
Yeah. Yeah, it's pretty straightforward, like right now.
Okay. Yeah, I'm moving very, very slowly, so you understand everything, because this is really important for the rest. So this was dialectics. We introduced the concept of polarization vector, right? The dense bound charges and their density and the current, and we introduced polarization, we introduced the dielectric permittivity, and when we change the matter from free space to some material, right, we substitute the epsilon 0 by epsilon 0 epsilon. But this is for dielectrics. And what about other materials, for example, magnetics? So magnetics, materials that react to the presence of magnetic field. So if a matter reacts to the presence of magnetic field, then the material is magnetizable. Then the material is magnetizable. And we're talking about magnetic polarization. Magnetic polarization also known as magnetization. 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 So how we describe this process of magnetization? So in the case of dielectrics, we introduce this concept of electric dipole moment that allowed us to go to generalize this to the number of atoms, introduce the concept of polarization vector, and then build this theory of electromagnetic field and dielectrics. So now, as for the magnetics, the material for magnetizable materials, we introduced the concept of magnetic dipole. And a magnetic dipole is a small loop current. Okay, so it's like a small coil with a current, I small. And of course, this loop is somehow oriented in the space, and we need to define the way we orient this plane of the loop in the space, right? So I introduced the oriented area. So the area we denoted by ds, and the way we orient this area, we define the orientation of this area is by the normal vector to the area, right? So I is the current, ds is the oriented area. It's a vector. And the magnetic dipole moment m is simply the product of the current and the oriented area, like this. So this is magnetic dipole by definition. Okay. So if magnetic field is applied, the all magnetic dipoles in such a magnetizable material align preferably along this magnetic field. And this is the process of magnetization. So if magnetic field is applied, all magnetic dipoles, elementary magnetic dipoles align preferably or mainly along magnetic field vector, and hence this magnetization. Magnetization. Well, why loop current? Because this is elementary magnetic dipole. The loop currents like this is a model for example, orbital movement of electrons around the nuclei, right? They orbit around the nuclei, and this orbiting creates the loop current, and this loop current manifests itself as the magnetic dipole. So if you have some atoms with electrons that orbit around the nuclei, you apply magnetic field, and these atoms, they change their orientation along the magnetic field direction. Okay, and this is the magnetization. And of course, if we have a system of n capital atoms like this, we've got the m capital, which is magnetization. M capital magnetization is equal to n times n small. And without much derivations, we just add this magnetization vector to the definition of B, which is the B magnetic field, which was equal to mu 0 H. Right, so now I add this magnetization to this formula here. Okay, so the fact that the material can be magnetized leads to this new term in this formula. Like this. So again, usually this magnetization vector is proportional to the value of magnetic field. Okay, and this alpha m is the magnetic polarizability, magnetic so it's just another parameter like alpha E for electric polarizability, for electric polarization. In this case, for magnetization, we have magnetic polarizability, factor that describes the ability of a matter to be magnetized in the magnetic field. Yeah, plugging in this one to the formula above leads to this new one, mu 0 mu H, with mu equals to 1 plus alpha m. Okay, so the result is similar. So if you have a material that is magnetizable, what we do, we replace in all equations in free space, we replace mu 0 by mu 0 mu in all equations in free space or dielectric. We replace mu 0 by mu 0 mu. However, there is one important note. Magnetization through rotation of these magnetic dipoles is usually slow process. So usually the magnetization is slow because this rotation, it takes some time, and if the direction of magnetic field changes in time, the magnetic dipoles cannot follow this change of the direction of magnetic field because they too slow to do so. Especially if we dealing with the fields that oscillate or change at very high frequencies, for example, in optics. And as a result of this, as a consequence of this, we have no or almost no, I write no magnetization at higher frequencies. No magnetization at higher frequencies or high frequencies. for example, in optics. So it's a known fact that in optics, materials don't demonstrate any magnetic effects, no magnetism in optics. And this is exactly for this reason. This rotation of magnetic dipoles, it needs time. And if the field oscillates too fast, then in average, the magnetic dipoles, they don't change. So in optics, mu is equal to 1. At the same time, in microwaves, terahertz, radio waves, the most of the used materials, they also non-magnetic. So we are not gonna do any simulations of the magnetic materials for this reason. So in optics, we have no magnetism, no magnetic effects. In microwaves, terahertz, radio field, most of the materials are non-magnetic. In microwaves, RF, etc., are the most of materials are non-magnetic. Non-magnetic. And we won't discuss these these materials in what follows. In fact, these magnetic materials, they used only in systems like Faraday rotators, polarizers, non-reciprocal devices, circulators, isolators. But usually they are they pretty lossy, so they have this dissipation effect as a price to their magnetization. They are lossy, and usually we don't use materials that can be magnetized for other purposes rather than their effects associated with magnetization. Okay. All right. And yeah, I also have these conductors, but I guess we will discuss this case next time. And also next time we will start using the numerical software. I will show you a couple of examples first, like showing my screen. Okay, and then in a couple of weeks we will start doing the labs. All right, so let me stop the recording.